Okay, this is Regents Chemistry Review Session 5, and this lesson will focus on kinetics and equilibrium and all about acids and bases. So let's talk about Le Chatelier's principle. Le Chatelier's principle tells us that when a system is stressed, the system will move in a direction in order to relieve that stress. And I explain to my students that it's kind of like taking one of those clown balloons that you can twist into shapes. And if you have that long balloon before you twist it before you, if you squeeze on the very right side of the balloon, the air is going to shift to the left side of the balloon. Why? Because you applied stress to the right side of that balloon. If I squeeze on the left side of the balloon, then the air will shift to the right. Because you increase stress on the left, the air moved to the right. Now, if I release my hand on the left side of the balloon, then the air will go back. So that's kind of what happens with Le Chatelier's principle. When you increase a stress, it shifts to the opposite side. When you decrease a stress, you let your hand off that balloon, it goes back toward that side. The only one that's special is gases. So gases we basically have to memorize. And with gases, that involves pressure. So with a gas, if I increase pressure, then the shift is to the side with the least number of moles. And if I decrease pressure, then it'll shift to the side with the most number of moles. If the moles of gas are equal on both sides of the equation, then pressure has no effect on the system. So let's look at this example we have here. What happens to the reaction above when the pressure is increased? Well, first of all, this is an all-gas system. Nitrogen is a gas, oxygen is a gas, and NO2 is a gas. So the first thing that I'm going to look at is I have 2 moles of gas here on the right, and I have 2 plus an unspoken 1 here on the left is 3. So when I increase pressure, as I just said, it shifts to the side with the least number of moles. So it's going to shift to the right. And when it shifts right, that means it's going to be making more NO2. So the NO2 increases. And how does it do it? Because N2 and O2 are colliding more. So if N2 and O2 are colliding more, that means they are decreasing. If the pressure is decreased, then it's going to shift to the left, the side with the most number of moles. And that means we're going to be making more N2 and O2. So that means they will increase. And your NO2 is going to decrease because that's going to be decomposing. Okay? When it shifts this way, the NO2 is going to break down and make more N2 and O2. So this will decrease. Now what about temperature? There is no temperature in this reaction, so let's go to table I and find this reaction. N2 right here plus O2 yields 2NO2. This is a positive 66.4. So a positive delta H means that it's endothermic. Endothermic. And if you forget that, you can look on the bottom of the table, all the way at the bottom, and it says a minus sign indicates an exothermic reaction. And this is on your reference tables too, so you don't have to worry about that. So when the temperature increases, so if I were to write this in, endothermic means it's on the left, so this is plus 66.4 kilojoules. So if I increase temperature, I'm increasing the stress. Remember, it's like squeezing the balloon. If I squeeze the balloon on this side, the air is going to go to the right. So it's going to shift to the right. And that means, again, we're making more NO2. So the NO2, they change the order now, is going to increase, and O2 will decrease, and N2 will decrease because they're colliding more to make the NO2. If temperature decreases, so if temperature decreases this way, then it's going to shift toward the decrease. So that means it's going to shift to the left, and that means NO2 is going to decrease because it's going to break down and it's going to make more O2 and it's going to make more N2. Now, what about if I increase NO2? NO2 is on the right, so if I squeeze the balloon on the right, it's going to shift to the opposite side. So that means it's going to shift to the left, and that means that we're going to have more N2 and O2 because the NO2 will break down. And N2, which is on the left, if I decrease the N2, remember it tries to replace it, so it's going to go toward the decrease. So it's also going to shift to the left, and NO2 is going to decrease because that's going to break down, and O2 will increase. What is the enthalpy? Enthalpy is another word for energy. So what is the energy for the decomposition of 4 moles of NO2? Well, when we look at this reaction is for 2 moles. And when 2 moles of NO2 decompose, it is going to release 66.4 kilojoules. So if this is the amount of energy for 2, then the amount of energy for 4 would be twice that. So 66.4 times 2 is going to give us 132.8 kilojoules. 132.8 kilojoules. So a lot of times with table I, on this one right here, you can see that it's, let's pick which one. Okay, so here they tell you when carbon and hydrogen combine to make ethane, it releases negative 84 kilojoules. So that negative means it releases 84 kilojoules. And I could say to you, how much would be released if 2 moles of ethane are formed? So if there was a 2 here, then what I would have to do is double that, and that would mean it would be 168 kilojoules are released. Sometimes they might ask you half, like here, this is for 2 moles of water being formed. They might ask for 1 mole of water, which means that you have to decrease it. About potential energy diagrams, remember when you go downhill, it is exo, so this is an exothermic reaction. When you go uphill, when your products are higher than your reactants, then it would be endo. So this is endo. Okay, which represents the heat of formation? Heat of formation is delta H, and it's calculated by the products, the potential energy of the products minus the potential energy of the reactants. So if this is our product line and this is our reactant line, then the difference between these two, this one and this one, is C. Which letter represents the energy of activation of the reverse reaction? Forward reaction is left to right, reverse reaction is right to left, so that would be letter F right here. Activation is energy is from the product line to the top of the activated complex. Represents the potential energy of the products. Potential energy of the products goes from the reaction coordinate to the product line, which would be letter A. Activated complex is right here, so that would be D. Letter represents the energy of activation for the forward reaction. That would be B, going from the reactant line to the top. Potential energy of the reactants goes from the reaction coordinate all the way to the reaction line, which would be letter E. And what regions would be affected by the addition of a catalyst? If I add a catalyst, the catalyst is going to go like from here to here. Okay? It starts where the reactant line starts. It finishes where the product finishes. All it does is lower the amount of activation energy by creating an alternate pathway. So things that will be affected are B, because now B is only from here to here. F, because now F is only from here to about here. And D is also affected because now the potential energy of the activated complex is lowered. So we've got B, D, and F. Factors that affect the rate of a reaction. The speed of a reaction depends on the number of collisions and the fraction of those collisions that are effective. Remember, in order to have an effective collision, okay, well, in order for a reaction to take place, we need to have the proper bond angle and the right amount of activation energy, EA. There are certain factors that can increase the number of collisions, and then which in turn will increase the rate of the reaction. Catalysts, we've already talked about. The temperature, if we increase the temperature, it makes particles move faster, so they collide more. Concentration. If we have more particles per unit volume, so it's like a packed elevator, so to speak, then you increase the number of collisions. The nature of the reactants. Ionic is faster than covalent, and the reason being is because when we put ionic compounds in water, they dissociate, so the bonds are already broken, so they only have to just reform and hook up with something else, so it goes faster. And the reaction mechanism, how the reaction takes place. And the slow step, which is really not important for this one, but the slow step is the rate determining step. We also have equilibrium, is the balance between two opposite reactions, and it can be physical or chemical. So we have phase equilibrium, which is solid to liquid and then liquid to gas. And technically, if you have a substance that sublimes, you could have phase equilibrium between solid and gas. For the example of like CO2 solid, which is dry ice. And another one is iodine solid sublimes to the gas state, which I've done a demonstration on that this year. And then we have solution equilibrium, solids in liquids and liquids in gases. And solution equilibrium happens when you have a saturated solution. And that's important that you know that. Solution equilibrium is represented by a saturated solution, and that's when the dissolving rate is equal to the crystallization rate. What factors enable a reaction to occur spontaneously under a given set of conditions? That would be two things. We need to look at energy and we need to look at disorder. So we need to look at enthalpy and we need to look at entropy. Systems tend to change from higher to lower energy states. So an increase in potential energy to a decrease in potential energy. Many chemical reactions release energy. Products have less energy than the reactants. So the tendency for reactions to occur spontaneously is when they are exothermic. So the energy factor for spontaneous reactions is exothermic, because that is low energy, and we want an increase in entropy. So an increase in entropy, which is disorder. So solid going to liquid or solid going to gas, any of those. Events leading to higher disorder, one could be an increase in temperature, which leads to an increase in random motion of particles, phase changes, as I just said. One thing about acids and bases is you need to recognize the molarity. You need to know how to put it in scientific notation, what it looks like. So if I look at this number here, I've got 1, 2, 3, 4, 5, 6. This is really 1 times 10 to the minus 6. Once you have that in exponent format, this tells you your pH. So the pH is actually 6. Remember that the pH scale goes from 0 to 14. So 7, less than 7 is acidic, and greater than 7 is basic, and 7 is neutral. The stronger you are, the closer you are to 0, the stronger it is, and the closer you are to 14, the stronger it is. So if the whole scale is 14, excuse me, if the whole scale is 14, 1 times 10 to the negative 6. So a 6 and what is 14, which is 8, so my OH is going to be 1 times 10 to the negative 8. So my POH is 8. So if my pH is 6, then this is going to be acidic. If you have a POH of 2, that means that your pH is 12. This is 2, so this is going to be 1 times 10 to the negative 12, and this is 1 times 10 to the negative 2. 12, a pH at 12 is basic. If you have a pH of 4, then you have a POH of 10. This is going to be 1 times 10 to the negative 4, and this is 1 times 10 to the negative 10. So a pH of 4 is acidic. And in this last one, you have 1, 2, 3, 4, 5, 6, 7. 1 times 10 to the negative 7. Should have written it here. 1 times 10 to the negative 7. And 1 times 10 to the negative 7. So POH is 7, pH is 7, so this is neutral. For the 3 reactions listed, list the conjugate acid-base pairs and whether amphoterism is present or not. Remember, if something is amphoteric, it can act as an acid or a base. So this is referring to the other theory. This is really Bronsted-Lowry Theory, and they refer to this on the Regents as the other acid-base theory. The other acid-base theory, in which case a Bronsted-Lowry acid is a H plus donor and a base is an H plus acceptor. So in this case, you have to see who's donating to who. So this is H2O and it became H3O. So the H2SO4 donated to this. So this is acting as the acid. The water is acting as the base because it accepted it. So conjugate acid-base pair number 1 is going to be, and therefore if this is the acid, this is the conjugate base, and if this is the base, this is the conjugate acid. So you've got H2SO4 and HSO4 minus, and over here you've got H2O and H3O plus. Down here, there's no amphoterism. Here you've got water. One of the waters is acting as an acid and one of them's acting as a base, and it doesn't matter which. So here we have H2O is donating to H2O. So this is an acid, this is a base, and this would be the conjugate base, and this would be the conjugate acid. So this is amphoteric because water, one acted as an acid, one acted as a base. So we've got H2O and H3O plus, and we have H2O and OH minus. Okay. Given the reaction HSO4 minus plus NH3 yields NH4 plus and SO4, fill in the first blank of each question, either Bronsted-Lowry acid or Bronsted-Lowry base, and then in the because it blank, put the operational definition. So, meaning accepted H or accepted proton, so on and so forth. So in this one, you've got H2SO4 donating to H2SO4. So H2SO4 is an acid because it donated an H plus to H2O. H2O is a base because it accepted an H plus from H2SO4. Now if we looked at this going the other way, because this is a reversible reaction, you've got H3O donated to HSO4. So H3O plus is an acid because it donates an H plus to HSO4 minus. And HSO4 minus is a base because it accepted it. It accepts an H plus from H3O positive. Okay. Which substance acts as an Arrhenius acid? Remember, an Arrhenius acid has H plus in solution. That would be this one. NaI is a salt, LiH is a metal hydride, NH3 is a base. Which solution will turn phenolphthalein pink? That means you need a base. So the only one that's a base here is LiOH. This is an alcohol. Carbon dioxide is a gas, and this is an acid. Which is a salt? A salt is a metal and a nonmetal, or usually a metal and a halogen, or a metal and a polyatomic. This is an acid, this is an acid, this is a base. There's my salt. Red litmus will turn blue when placed in an aqueous solution of, we're talking about a base. Hold on. So we're looking for a base here. Number 1 is a salt, number 2, OH. Metal and OH is a base, this is an alcohol, and this is an organic acid. Which formula releases H plus and which releases OH minus when put into water? So H plus is going to be released by an acid, OH minus is going to be released by a base. So we have two answers. Excuse me. Two answers, KOH and the organic acid. So this will dissociate into K plus and OH minus. There's the OH minus. And this will dissociate into CH3, COO minus, and H plus. And there's the H plus. Which relationship is present in a solution that has a pH of 7? pH of 7, my H equals my OH minus. so this is a pH of 7. A pH of 10 means it's going to be basic, so my OH minus concentration has to be greater than my H concentration, so that would be a pH of number 3. This is pH equal to 10. And a pH of 5 is going to be acidic, so my H plus would be greater than my OH minus. Write out the resulting reaction as a balanced equation that occurs when the two are mixed below. So I've got H2SO4 and KOH. Remember, when you mix an acid and a base, this is a neutralization reaction, and that is simply a fancy name for a double replacement reaction. You have two compounds, and they are going to switch partners and wind up with H2O and a salt. So this is neutralization. Underneath each compound in the finely balanced equation, write acid, base, salt, and water. So this is an acid, this is the base, this is water, and this is a salt. And the pH of this would be neutral because a salt is produced, so pH is 7. Given the compounds H2, CO3, and NaOH, what pH could it possibly have? Again, you have an acid and a base, and it's going to produce a salt and water. The Na is going to hook up with the CO3. Na's got a +1 charge, CO3's got a -2 charge. So when you drop and cross, it's Na2CO3, and then the H hooks up with the OH to make H2O. However, here we've got to balance this by putting a 2 here, 2Na, 2Na. That gives you 2 H's here, 2 H's here. So we need 2 H's here, so that's 4 H's. 2 O's, and we've got 2 O's. So this is going to be your salt and water. And this is going to be a pH of 7. And that's because salts are usually neutral. What color would be a solution with a pH of 6.9 if you were using bromothymol blue? Remember on your indicator table that these are ranges. So for example, with methyl orange, 3.2 or less is going to be red, and 4.4 or greater would be yellow. If I had something in this range, it would be a blend of the two colors. So anything greater than 3.2 but less than 4.4 would probably be orange. So we're talking about pH of 6.9 bromothymol blue. So 6.9 is in the middle of this range. So yellow and blue make green. What color would a solution be with a pH of 1.7 if you were using Brom-Kressel green? 1.7 is less than 3.8, so my solution would be yellow. Okay, and that's it. If I have time, I'll do one more, which would review, I believe it's redox and organic. I can't promise that I'll have time to get it done before the Regents, but we've covered most of the topics. And keep studying, keep working on those practice questions, and good luck on Tuesday, everyone.